Here is the title: Stabilization of Quasi-Static Evolution of Lattice Spring Models with Plasticity. This joint work, some of the parts are joined with, actually everything is joined with Gudoshnikov, some of the parts are joined with Dima-Rachinsky. And then what we consider, let me watch time. So I start at 12. So I will try to finish on time and shorter, faster, earlier. So this is a system of elastoplastic springs. We consider a one-dimensional material, which means that all one-dimensional elastoplastic material modeled by a system of elastoplastic springs with one-dimensional nodes. Each node, the coordinate of each node is one-dimensional in this talk. Ivan later we'll have a talk with 2- and 3-dimensional nodes. Here, the nodes are one-dimensional. Every spring is elastoplastic. It means, as in Elisa's talk, it has elastic. The spring, she didn't have springs, but I have same for springs: elastic component and plastic component. When the elastic when the stress of the spring reaches the elastic limits, the plastic component of the length of the spring starts changing. So that's how each of this spring works. Each of the springs, therefore, comes with some limits on the allowed stress. Beyond those limits, the spring, the relaxed length of the spring starts changing. Then this allows to model the plastic ingredient of the velocity of the plastic ingredient of the length of the spring using this discontinuous function. This discontinuous function, which takes all positive values when we are at the right limit of allowed stresses, and it takes all negative values for the velocity, because here you see P prime is in this set. It means that the velocity of plastic part of the deformation can take any negative value when we are on the left end of the allowed stress for the spring. If we consider what is written here, is same is this rule extrapolated to all springs. Not to just one spring, but this rule is doing the same for all springs. Then the next equation which describes our network is this next equation describes the geometry of the springs, how the springs are connected between one another. It's very simple. There is a matrix called kinematic matrix in mechanics, called the transpose of this matrix is called
incidence matrix.
How it's called?
Incidence.
Oh yeah, thank you. Incidence matrix in graph theory. So how this matrix is constructed? For example, take the spring number 2. Here is the spring number 2. This line. What we see, the left node is the node number 4, the right node is the node number 5. Therefore, the column number 4 gets -1, the column number 5 gets 1. Very simple. And same for all other springs. The connections are all coded in this matrix, capital D. The next rule is the next rule explains how the so-called displacement-controlled loadings are introduced. So displacement-controlled loadings are controls that lock lengths between certain nodes. So in this system of springs, you see two displacement-controlled loadings, L1. This L1 locks the distance between node 2 and node 3. And here you have L2 locks and controls the distance between node 4 and node 8. Okay, so to explain that quickly, so trying to move it. What is this? For each displacement controlled loading, we associate a path of springs, and then this path of springs gives, in terms of graph theory, gives us an incidence vector. So the incidence vector for this particular, it's not unique. We can choose different paths, but the path which is given in this graph is coded by the incidence vector on the right-hand side. What it says? It says this incidence vector is saying that this spring number 1 contributes negatively because it goes to the left, away from, increases the distance to the to our loading, and these green springs contribute positively. Therefore, spring 4, 7, and 5, they receive ones, 1, 1, 1 here in the incidence vector. And same vector for this displacement-controlled loading, and this matrix R is a combination of all incidence vectors. And finally, the description of this network of springs features the static balance. Static balance is just the balance of forces at each node. So at node 2, for example, we have to balance the stress coming from this spring, the reaction of displacement control loading, the orange ingredient. The blue ingredient comes from the spring attached to this node. And finally, we have an additional green ingredient. Green ingredient is the stress-controlled loading applied at this node. And this static balance means that we work in quasi-static framework. Quasi-static framework, we assume that static balance holds. Now I'm going to switch the slide. Are there any maybe questions at this point? Let's switch the slide then. All these rules, equations are also listed here on this slide. Okay, 10 minutes passed. Now I want to derive a sweeping process. Sweeping process is who considered Samir didn't introduce sweeping process. So sweeping process is a differential inclusion. At this moment, let's say, or maybe it's better to say, a differential equation with a moving constraint. A differential equation with a moving constraint. Such type of constraint is modeled through a differential inclusion called sweeping process. You will see it in a few moments here. We derive this. So when I have found this derivation, Ivan Gudoshnikov showed me how to derive this sweeping process from these 5 equations that looked like a miracle for me and like pieces of puzzle connected together. But now I'm trying to explain that this is not really the pieces of puzzles by some luck. connected together. But I finally understood that it's a rather logical way of getting something. So if you start properly, so we have to start from static balance. If we start from static balance, then what we see, this static balance is an equation of the form if oh, I'm trying to write, maybe I cannot write. I think it works someday. Ah, it's working now. Okay, so what is written here, we can view these two ingredients. They can be viewed as a vector B. This matrix D transpose R can be viewed as some matrix A. So what we have here is a R. This is different A, not this A in the beginning. Equals B. So we have a linear equation. We have a linear equation. And Fredholm alternative tells us when this linear equation is solvable for R. This matrix capital A is not a square matrix, and it has some kernel, some non-degenerate kernel. Therefore, this equation won't be solvable for any B. And Fredholm alternative tells us how to restrict the space, to which space the values of B need to be restricted in order that this equation to be solvable for any R. Which comes from reaction controlled, which comes from reactions of displacement-controlled loadings. So that's the main idea. That's the main idea of everything here. We are going to reduce to a certain subspace where we can uncouple the elastic deformation from the plastic deformation, and that subspace, that convenient, useful subspace, comes from Fredholm alternative, which is a subspace which ensures solvability of this linear equation for any R. And here are some details, and ultimately that's what I said. This like vector B, almost vector B, and some transformation of vector B, because since you have a little f here, the little f can satisfy this equation. This little f is the stressed control loading stresses. Since little f satisfies this equation, then this little f must be of this form, D transpose, some algebra, just algebra. But most importantly, ultimately, we have that this B, this term here, the space of this term is restricted. It must be perpendicular to a certain space, capital U, coming from Fredholm alternative. That's the main point. We get a subspace U such that this part of the static balance is perpendicular to that subspace U. And this is the subspace. Therefore, what it means perpendicular? It means that this ingredient here belongs to U perpendicular, to the orthogonal, to the subspace orthogonal to U. And this orthogonal subspace, specifically not quite this, but slight minor modification just for some technical convenience. This minor modification of the space U orthogonal will be the space where our sweeping process will develop. So this is the main idea. This is the main idea, but then there are many other ideas, but this is the crucial one. Then Since we got some space capital U, now we start to elaborate based on this space capital U. We got some space capital U, we got some space capital V, which are orthogonal in certain scalar product, which involves this matrix A minus 1. And since we have a decomposition of the entire space into a product of U and V, then this E plus P, the elongation, the total length, the vector representing the total lengths of springs, can be decomposed as U, the space U, plus some element from the space V. Any element can be decomposed as U plus some element from capital V. In particular, this E plus P can be decomposed that way. But it turns out that this particular G that we have here for the decomposition of E plus P gets some nice formula. We can compute it in closed form, compute it explicitly. But that's technical, just technical, not ideological. Now, next step is deriving the sweeping process. The main idea again in deriving the sweeping process based on these two facts. Now we have this dark blue fact. Now we have this dark blue, which I denoted 2, and we have this pink, which I denoted 1. So we have these two initial ingredients, achievements that we got. Now, using these two achievements, we are going to derive a sweeping process. And therefore, sweeping process will be not in the entire space because this C, it's left in the previous slide. This C, well, maybe I still show you. This C, where is that C? It was far away. So this C is a parallelepiped. This capital C is a parallelepiped which comes from a product of intervals of elasticity of the springs. So this is capital C, is a parallelepiped of dimension M. And the entire idea is that we are going to reduce the dimension of this sweeping process. I'm saying sweeping process, the dimension of this inclusion, let's call it inclusion. We will be able to reduce the dimension of this inclusion from little m to the dimension of this space capital V. That's why we obtained that space capital V. The space capital V is the space to which we can reduce the dynamics of this differential inclusion. And it turns out that the corresponding reduction on the subspace capital V will include only elastic elongation. Elastic, no longer plastic elongation. So how that reduction carries out? It's based on on this. I could now call it reduction formula for set valued analysis. We have lots of reduction techniques in dynamical systems. I would call that this is the reduction technique in set valued analysis. So if you have two normal cones, you have one normal cone here to some red set, you have a normal cone, blue normal cone to this blue set, then the normal cone for the intersection, this gray here is the intersection of the two sets. That normal, the normal cone to this gray region, as we see from the picture, will be exactly the union or the sum of these two normal cones. That is exactly what is written here. So if we sum two normal cones, then we get an intersection of the respective sets here. Intersection means reduction of dimension.
Excuse me, Oleg, do you have qualification condition fulfilled for this formula? It's not for free.
Yes. We have, first of all, we have here polyhedral sets, one condition, and secondly, they must intersect, the interiors, that's what you probably mean.
Okay, that's fine. Okay, thank you.
The interiors must have a common point. Yes, we have that all, of course.
Okay, very good, thanks.
Yes. But then the question is, now we want to use this reduction formula in order to reduce the dimension of this sweeping process. But we don't have any other normal cons here. We have just n capital C of S. And then we observe, then we introduce artificially this additional normal cone. We can say that we add to this we add some terms to the left-hand side, and we add some terms to the right-hand side, and the terms from the right-hand side here will be elements of the space U, and therefore we can replace since the spaces V and U, they are orthogonal complements, then that's another fact from set-valued analysis. The normal cone to V at Y will be the orthogonal, that's basically the definition of the normal cone, will be the orthogonal complement of the space. And that's how the second normal cone can be incorporated here, which gives us the reduction of the dimension in the sweeping process based on this nice reduction formula. Okay, and finally, what we get this sweeping process, this one, y minus y dot equals this, where this C of t is the intersection coming from here, coming from this formula. So the moving set of the set, I'm not saying yet moving, the set in our sweeping process will be some intersection. You see that I changed the variable, it's y, but it's just for convenience. It's not really essential. So what you see here is, for some reason, this is what Moreau did for convenience. So then you see that y, the way how y is introduced, it contains only elastic elongation, elastic. And these are known functions. G comes from displacement-controlled loading, H comes from stress loading at nodes. So these functions are known. They are known, and this is the elastic elongation. So if we can find y, then we can find elastic elongations. Okay, I have 4 minutes left. So what we get finally is the sweeping process whose constraint, we got a differential equation whose constraint is the intersection of this capital pi of t with a plane. Capital pi of t, by the way, based on this formula, you remember that this C is a parallelepiped. So we have a parallelepiped shifted. In other words, pi of t is a moving parallelepiped. And what is happening here is the intersection of the moving parallelepiped with a plane. This is the constraint of our sweeping process. Okay, it's illustrated here. So here is the parallelepiped intersected by some plane capital V. And this parallelepiped is moving. Okay, this brief illustration gives you the sense of how solutions of the sweeping process behave. So this triangle here, think of this triangle is as this C of t, the moving constraint. The moving constraint C, capital C of t, is this triangle here. It's written actually, very good, C of t. Now this yellow point is the initial condition of the solution of the sweeping process. Now I'm going to show you how this solution develops and how the solution of the sweeping process looks like relative to the displacement of this moving constraint. So let's displace it a little bit. So this, I'm moving it down, I'm moving the set down. So the point first sticks to the, and I swipe the point. The point doesn't, this point here does not ever escape and leaves some trace, The set is moving and moves the point, catches the point by its vertex. So this point is moving and leaves some trace, So this trace is a solution of sweeping process. So it moves like that, now like this, then now this point now slides along the boundary because set is moving a little bit to the right. Now this is the trace, the corresponding trace. Now the set is moving upstairs. Therefore, this set does not touch this point. So this point just stays, so this motion of the moving set does not contribute, does not develop more trace, doesn't develop this yellow curve. Now, finally, we reach the point where the displacement-controlled loading touches our point and moves it to upwards, and creates some more trace. So this is how the solution of the sweeping process will look like when you move a constraint. Here is another illustration of the same. Therefore, if we move our constraint, this intersection back and forth, then okay, this slide is showing that if we move our constraint back and forth, then we can get different types of solutions. For example, if you look at this at this type of motion of the constraint, when it moves just horizontally, then all the solutions will ultimately, and especially if you move it to the left for long, that way, then all points, all trajectories will stick to this corner at the end. So that means some convergence in to the vertex if may occur, and this regime will be unique. All trajectories will converge here. On the other hand, if we move this constraint this way, then there might be a family of solutions. All points from here will be initial conditions, and we showed that this situation might be structurally stable. Mathematically, it looks like you easily destroy this, but physically, no. If you perturb the system of springs, this situation may stay. Therefore, actually, everything might happen if you do not impose any additional conditions on this moving constraint. Everything is possible. But it turns out that if you know that your moving constraint is a simplex, this type of shape, then everything is predicted in a unique way all the time. There will always be a unique response to the displacement if this intersection of this parallelepiped with the plane is a simplex. In other words, so this piece here is a simplex. It looks like planar here, but this all is in higher dimensions. Therefore, this red triangle is actually this red simplex. And we proved that we might always have a simplex if under certain conditions, let's say simple conditions, when the motion of when the dimension of this set capital V is one less the dimension of the entire space, one less the dimension of this parallelepiped. The dimension of V, one less the dimension of this parallelepiped. But so we are still, yeah, it's still our plan to, and we still don't really know exactly how to do that, to understand the conditions for this intersection to be a simplex in the case when the dimension of this hyperplane is smaller, not of codimension 1, but of higher codimension compared to the dimension of the space. So one of the questions that we ran into, assume you could, if you, okay, maybe just briefly to explain, I of course don't have time. Briefly, we might first reduce that. Okay, briefly will be too brief. Okay, maybe I should just say that ultimately one of the problems is that we are getting is if we have higher codimension, codimension 2, for example, then we have a problem of intersection of a simplex with the plane. Codimension 2 means we might have, in certain sense, two vectors. Now, okay, probably this will all be unclear. Okay, simply, I can just say that in codimension 2, we have, this is one of the problems. So we need to know, in order to make some progress on that, in that question, we have to know when the intersection of a simplex with a plane is a simplex. That's one of the questions on that way. So basically, then I understand that I'm running 5 minutes late. But then I quickly, with the next slide. Any questions here? Maybe. Okay, now next slide here. Now let's assume that we what we considered in this slide was some cyclic excitation of the material. Cyclic excitation. What if we just move in one direction? Here, in this picture, moving to the left, just to the left. Then all points, as we mentioned, will stick to this corner, and regardless of what is happening on this end, we can forget about that and use just local condition for this stability to make sure that all regimes converge to this red point here. And so here we use the condition which Samir Adly also used in his talk. So what is required is that the vector of the motion of this displacement of this constraint, the vector of the velocity of this constraint at this point, in this corner, to be in the normal cone, to be strictly in the normal cone constructed at this vertex. So that's an assumption. If the velocity vector is strictly in a normal cone to this vertex, then all trajectories will approach this vertex in finite time. Of course, this is just a geometric result. What took us a lot of efforts is to apply this. Apply this to the system of springs. So how to rewrite this condition in terms of our network of springs. So this is our latest achievement. Again, the Rockefeller That's Now book helps. What we used from that book is that the cone, actually that's I used in my drawing already. The normal cone is the convex hole, or is the cone constructed based, or conic hole constructed based on the tangent vectors at this point. Each side of our constraint comes with its tangent or normal vector, and in particular this side has its normal vector, and this side has its normal vector, and therefore the cone at this point can be constructed this way. Now, how it helps? Now it means that we can compute the right-hand side. We can compute the right-hand side in this inclusion. We can compute this red set. But one of the first problems is that we get that these normal vectors, they are normal vectors in the space capital V. Is in the hyperplane, which is slicing the parallelepiped. These normal vectors must be found, must be computed. We need a computational algorithm to compute these normal vectors. This is done. Then we need to find this function g. You remember I mentioned earlier that we have a formula for this little g. So we have to find a formula for this little g. So after all ingredients, this ng and g prime are known, then we can plug them into this formula, into this Adly condition, and get the condition for finite time stability. And that's what took us lots of time to come up with the proper computations. So what we'll have here on the screen, so this formula ultimately takes this form for our system of springs. Oops, I lost my mouse, unfortunately. Oh, here it is. For this system of springs. I introduced almost everything. Okay, I didn't introduce this matrix. So this matrix is what? Is so the kernel. This matrix is the orthogonal complement of the matrix capital D. So the product of the matrix capital D with this matrix gives zero. Gives zero. That's the way how it's introduced. I will not go into further details. Mainly we were able to rewrite this formula in this form here, where all ingredients are from our initial system of elastoplastic springs. So I only have to stress your attention to what? So here we examine stability of this point, of this red point. Therefore, this red point is given by the two normal vectors. This one minus n with the index j1, and these normal vectors n with the index of j2. So then, and there are more indexes. There is a total, since the dimension of the entire space is m. Then we have a total. Since we have m springs, maybe that's better to say. Since we have m springs, and each of these constraints, each of these opposite constraints comes from a spring. Therefore, we have m pairs, m pairs of these normal vectors. And these indexes here are saying which normal vectors out of that list of m normal vectors are the normal vectors corresponding to this point. Therefore, every point, so therefore this vertex, to this vertex we can associate a list of indexes of normal vectors, which form this vertex. And this is the notation. This is denoted I0, and it appears also here in this equation. So therefore, this blue equation inclusion is saying in order for this red point formed by the normal vectors with the indexes J1 and J2, in order for this point to be finite time stable and attract all other points, this inclusion must hold. And this point is finite time stable means what? When we reach this point, then the spring J1 will be in plastic mode, and the spring J2 will be in plastic mode. All other springs will be in elastic mode. So from this inclusion, if it holds for I0, then we can make such a conclusion. And Joyson will also elaborate on this a little bit, mentioning the feasibility condition, which is still required. But I will finish at this point. Thank you very much.